Welcome, and thank you for joining me. My name is Sven Giesselbach, and I am the team lead of the Natural Language Understanding team at the Knowledge Discovery Department of Fraunhofer IAIS. I am also a researcher at the Competence Center for Machine Learning Rhein-Ruhr, short ML2R. And my research focuses on learning representations of text for natural language understanding, which is also the topic of this talk. In this talk, I'm going to introduce you to methods which enable us to learn meaningful representations of text for natural language understanding. The slides which I'm using are a joint work of Dr. Gerhard Paas and me. Together we give a course on natural language understanding at Fraunhofer IAIS. Why natural language understanding? Well, natural language understanding is a very interesting and exciting topic. It fuels many so-called AI applications, such as smart assistants. Siri, Alexa, and Google Now all use natural language understanding. But there are many other applications, such as the analysis of reviews on Yelp, the automated extraction of information in documents, and a complete understanding of documents requires natural language understanding. What are meaningful representations? Well, first of all, text representations are the features which we input into our machine learning models, most often neural networks. Meaningful representations meaning that they capture the meaning of words and the relations of words. Also, they should capture syntactical and semantical information. We are going to start off with classical approaches to text representations, such as the back-of-words representation and TF-IDF vector representation. Then we're going to look into distributed embeddings, such as Word2Vec, which is the most prominent distributed embedding approach. Word2Vec was introduced in 2013 and has revolutionized natural language processing and understanding. Together with neural networks, Word2Vec has improved the state of the art in almost every natural language processing and natural language understanding task. FastText is a modification of Word2Vec, which also uses morphological information. And Doc2Vec is a modification which learns document representations rather than word representations, or paragraph representations. It's also often called paragraph vectors. As last distributed embedding, we're going to look into Bipair embeddings. Bipair embeddings are very resource-friendly. They use less memory and disk space and have a significantly smaller vocabulary size. What's also interesting about them is that they are the input representation for many contextualized embeddings, such as BERT. Contextualized embeddings have increased the state of the art in almost every natural language processing and natural language understanding task today. They are the stars of text representations. We're going to start with Elmo, which is a BiLSTM-based representation. Then we're going to look into BERT, which is based on transformers, and a modification, which is distal BERT, which is also more resource-friendly, but we have to use resource-friendly in quotation marks here. Lastly, we're going to look into GPT-3, which is a monster transformer. It uses billions of parameters and set the state of the art in language modeling. In order to understand GPT-3, we're going to look at the GPT-2 first. I'm going to motivate all of these embeddings with applications. And these applications span from word similarities over document similarities to relation extraction and aspect-based opinion mining. And I'm going to do all of this with our NLU showroom. The NLU showroom is something that we've been developing, and we are hoping to release in mid-September or at the end of September. It's a website on which you can play with NLU models and can explore NLU tasks. You can see the weaknesses and strengths of different models. And we are very excited to show it to you. I hope I caught your interest. Okay, let's start with classical vector space representations such as back-of-words and TF-IDF vector representations. So we want to represent texts or documents in a way that computers and statistical methods can process them. And in order to do this, we are typically going to represent texts by numeric vectors of fixed length. A simple example of this is the back-of-words representation. In a back-of-words representation, we are going to create a vector and count each word in a document. So let's say we have the sentence Barack and Michelle Obama went to Paris and Bonn. Now, we take each individual words here, and it composes our vocabulary. So we have the words Barack, Bonn, Michelle, Obama, Paris, and to went. And now we simply count how often each of the words occurs in the sentence above. And we'll notice that each word occurs once, except for and, which occurs twice. And of course, normally our vocabulary would be much larger, so there would be a lot of zeros behind went. There would be other words. Now, if we have such a vector representation, we could, for example, determine the semantic similarity of documents by comparing those vector representations. And in the bag of words case, of course, many identical words means a high similarity. Now, let's look at another example. Let's say we have the two documents or sentences, the mouse eats the cheese and he puts the mouse on the table. Now, CWD represents the count of the word W in document D for every word W in our vocabulary. Now, if we count each word individually, we'll see that some words have a zero count, of course, because they only occur in the other document. For example, the word he only occurs in the second document, and the word cheese and eats only occurs in the first document. But what we'll also see is that there are some words, namely mouse and the, where we have overlap. So mouse occurs in both documents and the occurs twice in both documents. So this should increase the similarity of those documents, which is of course also troublesome because the word the doesn't contain any meaning in this case. If we create these vectors with all of the words in our vocabulary, the dimensionality of those vectors can easily be over 100,000 words, and much more. Many times we have more than 1 million unique words in our document collections, or corpora as we call them. Now what we can do now is take these vectors and normalize them to length 1. So we simply divide by the length. If we do so, we get lengths for both vectors, and we normalize both vectors by the length, and then we get these normalized vector representations for document 1 and document 2. And we could, for example, calculate the cosine similarity. And the cosine similarity would be an indicator for us as to how similar document 1 and document 2 are. If we get a value from 1, we know that the documents are the same, so they're very, very similar. If we get a value of 0, the documents are unrelated. We won't get negative similarities here because we don't have negative counts. Now I said that the TF-IDF vector representation is a bit smarter than the back of words representations, so it's not only counts. Instead, this representation gives more weight to words which carry more information. How does it do that? So it's composed of two things. The term frequency, which is essentially the bag of words representation which we already have. How often does a word occur in a document? And words that appear more frequently should be more important to the document. However, as we saw in the example before, the word the occurred quite frequently, but didn't have any information. So this is where the inverse document frequency comes into play. The inverse document frequency asks the question, how often does a word occur across documents? And of course, words which occur often across documents are not as meaningful. So, the, for example, is an irrelevant word. There are multiple ways now how to weight the term frequency and the inverse document frequency. One example, and a very popular example, is that we take the counts and multiply them with the logarithm of the total vocabulary size and then divide it by the amount that word occurs across all documents. But as I said, there are many different weighting schemes, and this is just one of them. Now, what are some problems with these representations? So first of all, they don't understand what synonyms are. So if we have the word car, automobile, convertible, etc., we would like them to represent a similar concept, right? And in the document representations that we saw so far, car and automobile, for example, would be two individual components of our vector. And if we have car in the one document and automobile in the other document, our cosine similarity would be too low because we wouldn't share any ones or any numbers in both vector representations. So the cosine similarity is too low if we have synonyms when we use the back of words or TF-IDF representation. Now we also have a problem with homonyms. What are homonyms? Those are words which have several meanings. So for example, the word mouse. Now if you think back of the example I gave, I said the mouse eats the cheese, which is clearly an animal, but he puts the mouse on the table. It could of course be the computer mouse. And we would have no way to distinguish this when we use back of words and TF-IDF vector representations. So mouse would in both cases have a 1, and we would think that it's about the same concept of mouse. But in one case we are talking about an animal, in the other case we're talking about the device that we're using. So in this case the cosine similarity would be too high if we have the same word with different meanings. Now we don't have any grouping whatsoever of words into semantic fields or semantic concepts if we use the back of words or the TF-IDF vector representation. And we need a different kind of representation in order to compute similarities which take into account the synonymity and the homonymity. Now in order to derive feature representations which also capture synonymity and homonymity, we're going to look at something called the distributional hypothesis. And we're going to start by looking at word embeddings, so word representations instead of document representations. In 1957, Firth published a paper in which he claimed that a word is characterized by the company it keeps, meaning that similar words usually occur in similar contexts, and if words have similar contexts, then they also will have similar meanings. Let's look at the toy example here. The child is playing in the sand, the mother lost her child, the child is crying. We could easily exchange the word child with the word kid in each of these sentences, and we would still have the same meaning. So that tells us that kid and child should have a very, very similar meaning, and if we create representations for both of those words, they should probably be very similar. So other than in back of words or in TF-IDF representations, there should not be one component for kid and one for child, but kid and child should be represented fairly similar. And remember, now we're talking about word representations. So if we derive word representations, we want them to be close together. And in these embedding methods, which we're going to look at now, the hypothesis is that words close to a word which we're trying to represent, our target word, are the neighborhood of this word. So we're typically just looking at a small window to the left and to the right of each word and say that this is the company that this word keeps, its context. So we're going to represent each word by a small vector of numbers. And words which have similar meanings should have vectors which are close together in the vector space. So kid and child should ideally be very, very close in the vector space. And in an ideal text representation space, they would probably have the same exact vector representation. Words which are closely related but not a synonym should be a bit farther apart. So the word boy or the word girl should be a bit farther from kid and child. And unrelated words like the word car should be even farther apart. There's one more important thing, and that is we can also calculate a difference vector between two words. And as we can see in some of these approaches, which we're going to learn about now, this direction of similarity also has a meaning. And there's some very cool properties of this. And if we have vectors of length more than 100, we have many possible directions of similarity and many ways and dimensions of coping with meaning. Now, the first distributed embedding technology which I want to present to you is Word2Vec. It has been introduced by Mikolov in 2013 and his team. And first of all, let's assume that every word gets an embedding vector of size k. So k might be 100, 200, 350, or whichever number you come up with. But typically in literature it's 200 or 300. Just for the sake of it, we're going to start with 100 here. Now each word gets assigned a 100-dimensional embedding. Of course, you can see only because of the simplicity, these are 3-dimensional embeddings here, but okay, you can imagine that these are 100-dimensional embeddings now. And in the beginning, we randomly initialize them. So every word gets a random 100-dimensional vector. Now, what we're going to do is we're going to take this 100-dimensional vector forward. We're going to try to predict its neighboring words. And how are we going to do this? So let's say we're at the words economics while processing the text. And now we train a logistic model to predict the word ERT. And what does this exactly do? It takes the vector representation of the word economics, and then it takes the representation of the word earned and all of the other words in our vocabulary, and it compares their similarity. And it maximizes the similarity between the words which really occur in the context of economics, and tries to minimize the similarity to all other words. So what we're going to do is we take the word of economics, try to predict earned, and degree, from, and go on. Next time I'm going to do this for degree, economics, from, Wharton, and as you can see, we take a neighborhood of 2 to the left and 2 to the right here. And at each step, we're going to calculate an arrow. We're going to propagate this arrow back, change representations for each of the neighboring words and for the central word. And this way, what's going to happen is that the vector representations of the center word and its neighbor words are pulled together, and the representation of words which are not in the context are pushed away from each other. And we will, of course, repeat this for all of the words in our document collection. And once this is trained, we obtain our vector representations. For this, we don't need any annotations. So this is something that we call self-supervised training. It used to be called unsupervised training, but Yann LeCun said that this, because it's training on the data set itself, we will call it self-supervised training. There's still some kind of supervision, right? So in the beginning, we pick a central word, for example, economics, and we look up the embedding for this word. As I said in the beginning, this is randomly initialized, and during training, these embeddings are changed. Now, when we look it up, we get a 100-dimensional embedding of the word economics. Now we select the neighbor word. So it could be the word which is after economics, it could be degree. And we're trying to predict this word. So essentially what we're doing is we map this vector of economics onto the whole vocabulary and calculate similarity scores. So the score of how similar is economics to degree, how similar is it to any other words in the vocabulary. And then, of course, these similarity scores are in the size of the vocabulary that we have. Could, for example, be 50,000, but it could also be much more. So there are Google's Word2Vec models, for example, which have more than 1 million words in their vocabulary. What we do then is we convert these similarity scores into a softmax probability. That is, we take the score of the neighborhood which we're interested in, take the exponential of it, and divide it by the exponential of all of the scores of all of the other words in the vocabulary. And that way we're going to get normalized probability. And now what we want to do is we want to maximize the probability of the word which is really in the neighborhood and minimize the probability for all the words which are not in the neighborhood. And how are we going to do this? Or how is the algorithm going to do this? By making the representations of neighboring words more similar and words which are not in the neighborhood dissimilar. In order to change the words, we're going to calculate loss, namely the cross-entropy loss. And there we're going to compare the softmax scores with the one hot vectors of the real neighborhood words. Now the softmax has a very, very large denominator here because all of the words in our vocabulary are in this denominator. That means that at each step that we calculate these scores, these softmax probabilities, we need to go through the whole vocabulary here. And there are some tricks in order to cope with this. Namely, to approximate this score by sampling. And if we just pick a few negative samples, then we can approximate the true cross-entropy and the true gradient. And this is called the noise contrastive estimation, or also called negative sampling. And what we do then, if we calculate the losses, we use stochastic gradient descent, as is common in neural networks, and this is a very shallow neural network, to modify the weights of all of the words that we have, so namely to modify the embeddings. This is computationally very efficient, and it also works for larger corpora. Also, the stochastic gradient descent escapes local minima. And if you want to know how efficient this is, on a machine with, for example, 24 cores, you can run this through Wikipedia in a couple of hours. Now, if we get these embeddings, what we also get, of course, is this embedding space, and there are multiple ways of evaluating how good these embeddings are. One way, of course, is to simply do an explorative analysis. So we could map those vector embeddings into two-dimensional vector space, and we could, for example, see that the words which belong to sports have very similar representations, science words have similar representations, and so on and so forth. So we can very well deal with similar words and with synonymity here. One other very cool thing is that Word2Vec also captures relations between words, or relationships. And it was a big surprise when Word2Vec was released that this algorithm is able to do this, because it was not explicitly trained to do so. So the most famous example is, you take the embedding vector for the word king, you subtract the word man, and then you add this difference vector on to the word woman. And what you end up with is the representation of the word queen, or at least you end in the proximity of this representation. And this is really cool. So you can do vector arithmetics here with words. And as has been shown, you can do this for many more analogies. So USA to dollar is like UK to British pounds. And they found many more such relations which were captured by Word2Vec. And in early papers after Word2Vec was released, such relationship questions were used to evaluate the quality of word embedding representations. And they would be composed of questions such as Athens is to Greece as Baghdad is to Iraq, for example. And these benchmark data sets contain more than 19,000 such questions. However, these questions are heavily criticized, and although it's really impressive to see that Word2Vec trained, for example, on the text8 corpus, which is a small fraction of Wikipedia, already scores 40% accuracy here after 50 epochs, this is not a very meaningful benchmark for us. Because what's more interesting for us is, one thing, of course, how can we obtain similarities from this, but how can we use these representations to perform natural language processing or natural language understanding tasks? And that is a more meaningful benchmark. Now, I promised that we are also going to look into Doc2Vec, which is a slight modification of Word2Vec. What you've seen up till now is the skipgram version of Word2Vec, in which we take the central words and we try to predict the neighboring words. Word2Vec can also work the other way around. You take the neighboring words and try to predict the central words. And essentially, in this version of Doc2Vec, we're going to look at exactly this. So, again, we have vector representations for each of the words which we have. In addition, we have a paragraph vector. And now, one special thing happens. Over each context that the algorithm goes, it also drags this paragraph vector representation. And now, it will take all of the neighboring words, such as Trump, earned, economics, degree, to predict n, but it will also take this paragraph vector representation. And again, it will try to predict the vector, or to predict the word n, by generating a vector of the context which is very close to the word representation of n. What's special here is, first of all, because we take multiple words in the input, we have to find some way to aggregate them. So if you could, for example, take the sum, or more common, take an average of these vector representations. But what is very important is that every time you do this with Doc2Vec, you also take into account the paragraph vector or the document vector of the current document you're looking at. And by training the model like this paragraph embedding will start to capture the context of the whole document, because it's used in the prediction of every word in the whole document. There are very efficient implementations. There's a TensorFlow implementation, Me personally, I would recommend the Janssen representation also for Word2Vec. And Doc2Vec was introduced in 2014 by Le and Mikolov. Now we have a simple representation for documents, which is way more powerful than the back of words and TF-IF representation we looked at in the beginning. This representation is able to capture synonyms, right? So if we have the word Trump and if we have the word president, it would understand that these words are very, very closely related. As I said, we're going to look at the modification of Word2Vec, which also uses morphological information. And this is also very important, because Word2Vec and Doc2Vec, as I presented them, are not able to represent unseen or unknown words. Now, in FastText, which is the extension I'm talking about, which was released in 2017 by Boyanovsky, and also Mikolov was involved here, each word is represented as a bag of character engrams. So what are character engrams? Let's look at the example of trigrams. If you cut the word where into three trigrams, we get the trigram WHE, HER, ERE, and you see here that there are two more, the bracket in WH and RE, and greater sign, or the closing bracket. And what this means is we're going to cut each word into character sequences of certain lengths, could be 3, 4, 5, whatever. But we're also going to add starting and stopping symbols for every word, so that we know where a word begins and where a word ends. And why is this important? Because we want to have a different representation for the word her than for the trigram her, right? Because this is a part of another word, and here this is a complete word. And in addition to using these character engrams, if possible, we will also use a complete representation of a word. Why do I say if possible? Because if we haven't seen a word during training, we can still create a representation of this word by omitting the representation of the whole word. And now what we do is, for each word, we train an embedding again, or we start by defining an embedding. And for each character engram, we also define an embedding. And we represent the word by the sum of its engram embeddings, and if the word has an embedding, its own embedding, of course. And then, instead of predicting the context only by using the words themselves, we also use the character engrams for the prediction. So this is added here into the softmax calculation, but we also use the parts, the engrams of the characters. Now, as before, we can look at a small toy example. And here you see that the word economics has been split into eco, nom, x, and so on. And the same goes for degree. And this time, instead of only predicting the words, we can also predict the character engrams. Or we can also use the character engrams to make the predictions. What we're seeing here is very similar to the SIBO approach. This is the approach that we introduced with Doc2Vec. So the approach where we take context words, aggregate them, and predict the neighboring words, or the sample word. Now, the results of FastText show that it performs as good as Word2Vec if we have semantic analogy questions, such as man to king is as woman to queen, and it performs way better in most of the syntactic questions, such as run to running is as walk to walking. And this is not a surprise, because these syntactic questions, they rely more on morphology of words. The semantic results are slightly worse, so this is the column which indicates the FastText results, and these are Word2Vec results. Slightly worse in most of the questions and most of the languages, but the syntactic performance is often way better, so magnitudes better. FastText is also available as a free download. The source code is in C++, but there are also Python wrappers, also officially by Facebook, and they are pre-trained word vectors for over 157 languages, which you can download and use freely. And this is a really great resource if you want to start for querying similarities of words, or if you want to create document representations, or if you want to use them for downstream tasks, such as classifications. So FastText also comes with a classifier, and a very good performing one. Now, the last kind of embedding which I want to present is the Bipair embeddings. And we're going to start here by introducing the Bipair encodings. And Bipair encodings differ significantly from the previous approaches by how they create a vocabulary. Because now, not every word needs to be in the vocabulary, but rather character sequences compose the whole vocabulary. And what we're doing here is we first select all characters as tokens in our vocabulary, so all possible characters in our texts. And what we do then is we count how often each of those characters occurs, and we merge the most frequent ones. So here we have the vocabulary EINORST underscore, which separates words here. And then we merge E and I. Next step, we merge N and E. What you can also see is that we preserve the original vocabulary. And we're going to do this now repeatedly until the vocabulary has reached a prescribed size. Typically the size here is 60,000, 64,000. What happens now is that the most frequent words are explicit. So eine, for example, here, which is a very frequent German word, will have its explicit representation. All other words can be represented by their parts, so we can compose a word by its character engrams, by its character parts. And this is how we can represent arbitrary words, which can also be unseen in training. So similar as FastText, we can also derive embeddings for unseen words. Now we can easily compute embeddings for Bipair encoding. For example, if we use the tokenization, which we have to do through the Bipair encodings, and then train a Word2Vec model, or a very similar model, which is called GLOVE. And these pre-trained Bipair embeddings, they work surprisingly well, although they are composed of such a strange vocabulary. As you can see on the right, we can, for example, query for the word or the ending ingen, which is a suffix which is often used in cities in Germany. And you can see that we have other suffixes as most similar, like Hausen, Lingen, Hofen, and so on. So the similarity search really works here. And what's even more special, and I promised that this would be resource friendly, these embedding methods, Bipair embeddings, produce way smaller embedding files. So just to give you a comparison, for a named entity recognition task, an 11 megabyte Bipair embedding English model matches the results of a 6 gigabyte FastText model. And again, this embedding procedure, which was introduced by Sanders et al. In 2016, is also freely available. So you can download this and compute Bipair embeddings, which are going to be playing an important role in the contextualized embeddings, which we're going to look at in the next slides. Now, before starting to look at contextualized embeddings, let's first look at an application for distributed embeddings. One thing that we built into the NLU showroom is the ability to query for similar words using multiple embedding methods. So right now we have a model for Word2Vec, GLOVE, and FastText. We'll be adding others like Bipair embeddings soon. Why is this useful? Well, we could use it for terminology building. In one of our projects in the medical domain, we had the topic of colorectal cancer. And at the beginning, we wanted to create a terminology so that we knew when documents would be relevant for the medical doctors. And what you can see here is if you query for the word tumor in German, we will get a lot of different answers in Word2Vec, GLOVE, and FastText. And you can also see that FastText lays an emphasis on morphological similarity. And also something very interesting, it has this malign tumor, which contains the word tumor as well. And this is very different to the results that we get from Word2Vec and GLOVE. Another thing which is of course interesting when we look at document embeddings is document retrieval. So given a document, we want to find the most similar target documents. And one thing that we implemented here is, of course, Doc2Vec and something called the word movers distance, or in this case, word mover similarity. We take Word2Vec embeddings, GloVe embeddings, or FastText embeddings, and calculate the similarity of documents. And these sentences here are our source sentence. Es geht um einen Mangel bei der Bestellung des Monitors von ISO. So there was a mistake when we ordered this monitor from ISO. There was not a mistake, but there was a problem with the monitor that we ordered. And then the target sentences with which we want to compare this to are the display that we ordered was defect, had a defect. The other one is there was a lack of vitamin B. And if you look at this more closely, you can see that the second sentence here and the source sentence, they share more words. But the meaning of the words of the first target sentence and the source sentence are, of course, closer. And luckily, this is also reflected by the different similarity measures here. Some of them, like Doc2Vec, do it very well, while others are struggling but still picking the monitors, in both cases here, as the more similar sentence. Now, I think it's time for our first question. And this question is about FastText versus Word2Vec. So question 1. Which advantages does FastText have over Word2Vec? A. Unknown words can be represented. B. The algorithm needs less resources. C. Syntactic information can be captured better. Or D. Semantic information can be captured better. I hope that was not too hard. So let's look into contextualized embeddings. And first of all, what are the differences between distributed embeddings and contextualized embeddings? So embedding methods like Word2Vec, FastText, and BPE are referred to as distributed embeddings. You have now seen them. They have a single embedding per word or per character sequence, and this is learned over all contexts. And it's very good methods in terms of nearest neighbor retrieval and capturing relations between nearest neighbors, or words in general, but it's not ideal for downstream tasks. So even though Word2Vec increased the performance of many approaches in natural language processing and understanding, contextualized embeddings, these newer types of embeddings, are way better for downstream tasks. And what they do differently is that they learn embeddings per context in which words appear. So we don't have a single representation for a word, but we have a context-dependent representation. So we have multiple representations for each word, depending on the context. And these contextualized embeddings tailor the embeddings of a word towards the context. And this is, for example, good if we want to resolve the problem of homonyms, which we didn't quite resolve with Word2Vec. So with Word2Vec mouse, we still have just one representation, unless we modify Word2Vec a little bit. But with these contextualized embeddings, we would get very, very different representations for the mouse eats the cheese, and he uses the mouse to control the computer. What these contextualized embeddings are based on are language models. And these language models you all know from your smartphones. Let's say we have the sentence, the cat sat on the, and based on this part of a sentence, you want to predict the next word, which could, of course, be met. Now, what we want to do is we want to compute the probability of the word met given this context, and of course we want to maximize the probability of the word met given this context. So this is still very similar to the Word2Vec paradigm which we looked at, where we predict a central word. Now we're predicting a last word or a following word. And this is of course used in smartphones to predict the next word. So if I'm typing I'm going, it should automatically tell me that maybe the next word could be home or to or something similar. Language models can, for example, be deep neural networks, or are nowadays deep neural networks. And they also, of course, have, again, fixed length input vectors and output vectors. And in order to handle sequences of varying length, we need something different than we had until now, namely recurrency. So the idea is we have a neural network, we try to predict a word with this neural network with vectors of fixed length, and we store the information about the past in a hidden vector, as it is done in recurrent neural networks. And with the hidden vector and the current input, we try to predict a new hidden vector and the next input or the next output. We're going to repeat this for each element in our sequence. So this hidden vector is kind of a history of what we have seen already. X is our current vector, what word are we currently looking at, and then we're trying to predict the next word. So let's look at how this works with recurrent neural networks. So in the beginning we have a hidden vector which is initialized to zeros. And we have, for example, randomly initialized embeddings. But these could also be Bipair embeddings or Word2Vec embeddings for each word. Now, what we're doing now is we're going to input the hidden vector and the first embedding vector into our recurrent neural network. We're going to try to predict that the next word is cat. So the and then cat. And how we're going to do this is very, very similar to Word2Vec. So we have a softmax over all of the vocabulary, and we're going to maximize the probability of the word cat and minimize the probability of all other words. We're going to do this for each word at each position. And there's an arrow missing over here. There should also be an arrow from this vector into the recurrent neural network, of course. And this hidden vector here should now capture the context the, while the next hidden vector should capture, hence the arrow, the words the and cat, and so on and so forth. And now again, at each part we're training a logistic classifier, the softmax, to predict the correct word. And in the end, we obtain the probability of the word met, given the context the cat said on the, which is here represented by the embedding and the hidden vector 4, which should capture the whole context up till then. After this has been trained, we have hidden vectors after each embedding that we input, which should have a meaningful representation of the context. And because we're using recurrent neural networks, they should potentially also capture relations between very distant inputs. Important here is that this recurrent neural network stays the same at each position here. So it's not different recurrent neural networks, but it's the same one which has been trained at each of these positions and shares the parameters. Again, we need no manual annotation, so this is very similar to Word2Vec. We're just doing self-supervised training on the data itself. Now, Elmo built upon this hypothesis that each of the hidden states of the recurrent network can serve as a contextualized embedding of the words. And Elmo stands for embeddings through language modeling. And in Elmo, we stack multiple LSTMs, which are recurrent neural networks, upon each other. And instead of using single directional LSTMs, we'll use bidirectional LSTMs. So LSTMs going from the left to the right and from the right to the left through the text. Meaning that we can capture the right-hand context and the left-hand context of words. Instead of just using one hidden vector to represent the word the, for example, we're going to take the left-hand context and the right-hand context, and then we're going to have multiple LSTMs, for example, 2 layers of LSTMs, and we're going to use each of the representations created by these LSTMs, as well as an input representation, which could of course be, for example, Bipair embeddings. And now what we're going to do is we're going to pre-train Elmo as a language model, bidirectional language model. And then we're going to specialize Elmo to solve certain tasks, for example, named entity recognition, in which we try to, for example, understand which words belong to the name of a person, which words are the name of an organization, and so on. And what we're going to do there is we're going to take the different representations that we obtain for words in Elmo and learn a linear combination of them to better solve a task. So what we do is we have this first initial embedding of each word in the lowest layer, and then we get the bidirectional representations at each layer. So one representation from left to right, one from right to left, and we're going to stack them, and we're going to have this for multiple layers. So t greater or equal to 1. Could be 2, could be 3, could be multiple. And we're going to train these hidden vectors by training a language model. And once we're done training a language model and we want to train a downstream task, such as natural named entity recognition, we are going to process a sentence, which we want to recognize the entities in with Elmo, the language model. We're going to obtain the different hidden representations, so the different embedding representations for each word. And then we're going to learn a linear combination of all of them. And we train the weight of each of these representations by optimizing it on a task which we are performing. So for example, for entity recognition. And Elmo explicitly tackles this problem of polysemy because of homonymy. Now we have different meanings for words in different contexts. So now explicitly the word mouse will have two different embeddings in the context the mouse eats the cheese and the mouse is used to control the computer. These deep contextualized embeddings, Elmo, have been introduced in 2018 by Peters and his colleagues. Elmo showed great results on many tasks, natural language understanding and natural language processing tasks, and improved the state of the art on almost all of them. And what also has been shown is that if you use the representations of Elmo for the word play here, in this context, for example, you will get very, very meaningful nearest neighbors, that is, other contexts in which the word play occur, which show this disambiguation. So the model understands differences between the word play as in playing and play as in theater play, which Glove or Word2Vec, for example, couldn't. So they would recognize all of the words related to play as in theater play and in playing as similar. Now, what are the characteristics of Elmo? So as I said, it takes into account polysemy or homonymy, so different embeddings for the same word. It is highly contextual, so it means that the representations of words depend entirely on the context which they're used in, and of course on the initial representation. It is a very deep representation as it uses multiple bidirectional LSTMs. It is often used with character-based submodels of words, so for example Bipair embeddings, and it is also freely available from LNLP. And I'd recommend you to check out lnlp.org because they also have this website in which you can check out different methods from natural language processing, natural language understanding, in the English language. Now this leads me to question number 2, which is about Elmo. Which of the following statements about Elmo are true? A. Elmo contains exactly 2 bi-LSTM layers. B. Because of the contextualized embeddings, homonyms have different representations. C. Elmo cannot represent unseen words. D. Elmo is trained as language model and then specialized in a different task. Now, when it was released, Elmo was the star of the show. But unfortunately for Elmo, shortly afterwards, BERT was released, and it took the crown. And BERT relied on something which is called the attention mechanism, which I'm going to shortly explain by using LSTMs again. But BERT actually completely omits recurrent layers. So this attention mechanism was introduced in a translation task. And the task here was, or the setting here was that we had a sequence-to-sequence model which encoded a sequence in a source language and tried to decode it then into a target language. You can imagine that the encoder is something as a bidirectional recurrent neural network, or in the case of Elmo, a bidirectional LSTM. So again, a recurrent neural network that passes through a sequence from left to right and from right to left. In each position, it produces a hidden vector. And as we've seen in Elmo, these hidden vectors can be viewed as embedding representation, contextualized embedding representations of words. If you concatenate the left-hand and right-hand representation, we get a single representation for each word in each context. And this representation should contain information about the preceding and following words. However, it should be focused around the word that we're currently investigating. Now, the encoder will produce an output, which is a single hidden vector, of course. And this would be a bottleneck, because this single hidden vector has to capture all of the information of all of the words in sequence before. And to avoid this, the attention mechanism was created. And the attention mechanism basically allows the decoder to attend to every hidden representation produced by the encoder. And this looks something like this here. Now we have a decoder which can have different states, and at each position we can compare the decoder state to all of the hidden representations of the encoder and calculate a sort of correlation between the decoder state and the hidden representations of the encoder. And this correlation can be calculated in different ways. However, if we calculate this correlation, we take the weighted hidden representations, weighted by their correlations, and sum them up, and we get a context vector which is trimmed towards the current state of the decoder because of the similarity of the decoder state to the hidden representations. And we can also use this context vector in our decoder to produce better outputs. Now, this correlation is calculated with the softmax. However, the scores can be calculated in different ways. They could, for example, be cosine similarities, or normalized or scaled dot product, the dot product itself, or anything else you can imagine. Now, what's really cool about this attention mechanism, as we can see in the translation here, is that it also shows you at which points of the decoder which parts of the encoder are important. And you can really see that the architecture is able to map the proper words from the target language to the source language. Now, so far we've only seen attention in BILSTMs or recurrent neural networks, but I said that BERT does not use any recurrent neural networks before. So it only relies on transformers. And transformers consist of something called the self-attention mechanism. And BERT is basically the encoder part of such a transformer network. So what is self-attention? This is very interesting. Let's say we have the sentence, I am a student. And of course, we can derive an embedding for each of those words, for example, by using the Bipair embeddings that we introduced earlier. Now, the transformer architecture introduced by Vaswani et al. In 2017 introduces a query, key, and value matrix, or actually multiple query, key, and value matrices. And now let's say we process the word M. The word M is then transformed into a query representation, key representation, and value representation, as are all the other words. Now we're going to use the query representation of M and score it against all of the key representations of the other words in the context. And we're not just going to look like in Word2Vec, 2 to the left and 2 to the right, or 5 to the left and 5 to the right. We're going to look at the whole context, that means the whole sequence which we're currently processing. Now we obtain scores, which we can of course normalize with a softmax. And when we normalize them, ideally they should add up to 1. I think that looks good here. And we can use these normalized scores as weights. And then we take the weighted average of all of the value representations of all of the words here and construct a new representation for the word M, which is based on the context. So without using recurrent neural networks, we process the sequence here and contextualize this embedding. And we get a new contextualized embedding for the word M. And instead of doing this only once, we can do this multiple times, and of course for all of the words. And what is so nice about this transform architecture is we can do this essentially in parallel for all of the words here. So this is highly parallelizable. And in the transformer architecture, we have an encoder and a decoder, which mainly contain these multi-head self-attention layers. Multi-head meaning that we have multiple of those query, key, and value matrices. They also have fully connected networks and normalization layers. in the encoder. And remember, BERT only consists of the encoder. We're also going to look at the decoder. Now, there's one thing that should bother you. In the self-attention, we looked at all of the words in context. The decoder, of course, can only attend prior inputs, but it can, of course, also attend inputs from the encoder, as we've seen in this translation case. But since it's only able to attend prior outputs of the decoder, and not the future outputs, of course, we have something called a masked self-attention layer, which masks out future inputs. This looks something like that. And word 10 may only attend to words prior to the word 10. Now, one thing that's special about the decoder here is also this encoder-decoder attention, because instead of only the self-attention, so instead of only processing the sequence itself, it can also attend to the encoder states. And in the transform architecture, it attends to the last states of the encoder. Now, there's a block called the illustrated transformer, which contains a very, very illustrative visualization of how the transformer networks work. In the lowermost layer, we have the words, je suis étudiant, and their embeddings. And one important part, which we omitted up till now, is that we also have embeddings for time signals. What does that mean? We have an embedding which encodes the position of each word in the sequence. Why is this important? It's important because this way, without the recurrence that we had in the current neural networks, we know in which order the words appear. Because if you remember the self-attention correctly, it did not really matter where words stood. It just compared the key and the query of words no matter what the order is. But with this time signal, we can give it an idea of at which position of a sequence a word is. Now, what we're doing is we're adding the, for example, Bipair embeddings and this time signal embeddings, and we're pushing it through our encoder, so through our self-attention layer and normalizing layer, and typically we have multiple of those encoder layers. And then we get new encoded representations of je suis étudiant, which the decoder can then attend to and try to decode this into the language English, for example. And in the first position, it can, of course, only attend the outputs from the encoder. But in the second position, it can also attend to its first output, to I. Of course, not to future outputs, hence the masked attention. So the decoder has attention to the encoder and its prior outputs. Now, the transformer was an attention-only encoder-decoder model of, in the beginning, used for translation. And back then it was a very, very complex architecture consisting of 6 encoder layers and 6 decoder layers. And training took around 3.5 days on 8 P100 GPUs. Well, instead of processing sequences from one language into another, we could of course use these transform architectures also as language models. And the state-of-the-art architectures nowadays are all based on language models. So we have this new paradigm for natural language processing and understanding in which we train a language model on a large corpus of texts without annotations, so self-supervised training. We obtain context-sensitive embeddings, which know the structure of language. And for examples for this are Elmo, as we've already seen, but also BERT or OpenAI GPT, which we're going to look at later. And then we specialize these models on certain tasks. And this is namely transfer learning, right? So we have this language model which learns the language representations, and then we transfer the language knowledge that we have onto a task, so that we require less training data than before. And these contextualized embedding language models have shown significant increases in performance for many tasks, such as translation, relation extraction, sentiment analysis, and so on. And as already mentioned, the Hugging Face Transformers repository is a very, very good resource for many of the architectures mentioned here. Now, Word2Vec is also mentioned here Because Word2Vec, of course, can also be trained or is trained as a sort of language model and can then be specialized in downstream tasks by incorporating it in other neural network architectures. Now, BERT has already been mentioned quite a lot, and BERT also follows this paradigm of first training a language model and then specializing it on a certain task. BERT is based on the encoder part of the transformer model, the transformer architecture. So we omit the decoder here. And it modifies the encoder in some ways. So BERT has been introduced in 2018 by Delden et al. And it creates some special tokens for prediction tasks. And again, it's trained on large data sets, as was also Elmo. And BERT stands for bidirectional representations from transformers. Now, the special tokens which I mentioned are the CLS token, or classification token, and the separation token, and the masking token. And BERT trains a very specific language model. Instead of producing the next outputs, it's omitting some words in training and trying to predict which words have been omitted. So these are the masked words here. So most likely this here is to, and this here is bought. So the man went to the shop and he bought some milk. And in the pre-training step of BERT, BERT tries to predict the correct words at these positions here. BERT uses Bipair embeddings, for example, in the lowermost layer, and then poses them through some self-attention blocks, as we already know by the transformer architecture. And then in the last layer, it uses its contextualized embeddings to make predictions about the words missing, the masked words. So here it could be to, and here it could be bought. And again, we're using a logistic classification model in the end with a softmax to predict which words of the vocabulary are most likely to be at the missing positions. Now, in the training of BERTs, 80% of the time, tokens are replaced with a masked token. 10% of the time, tokens are replaced with a random token. And the other remaining 10% of the time, if tokens are altered, they're just left on, in that case, unaltered, so unchanged. One other task than the language modeling task that BERT does in pre-training is the next sentence detection. So this classifier token in pre-training is just here to classify whether the man went to the shop and he bought some soap are sentences which follow after each other. And if you look at the second example, the man went to the shop, cats eat mice, then it's very likely that this is not the next sentence following the first sentence. BERT is also able to capture long-distance relations. So if we have sentences following each other, because we're training in this way, we can also attend to very, very broad contexts. The only limitation that we have, of course, is our memory. How many hidden vectors or how many embedding vectors can we fit into the memory of our GPU? As already mentioned, BERT's lowest layer uses subwords tokens, so byte-pair embeddings, for example, or sentence part embeddings, in which words are split into subparts. And in BERT, in particular, they are split, and then we denote them with hashes if they are a part of a word. So we put these hashes in the beginning of a word part if the word part belongs to the word part before. Instead of only having these word representations, we also have these positional embeddings, which we mentioned in the transformer architecture, and we have these section embeddings, which indicate whether a token belongs to sentence 1 or sentence 2, for example. And BERT simply sums up these three representations for each token. Now, just as Elmo and the other language modeling approaches, BERT needs a lot of data for pre-training, large corpora of text. And if we train BERT, for example, on the books corpus, which is 800 million words, and English Wikipedia, which consists of 2.5 billion words, it takes, for the small BERT version, which is 12 encoder layers and a hidden size of 768 of the vectors, so approximately 110 million parameters, 4 days on 4 TPUs. On the large model, which is double the size in layers and 1024 hidden embedding size and 240 million parameters in total, it takes 4 days on 16 TPUs. So this is not resource friendly at all. There are many pre-trained BERT models available in TensorFlow, PyTorch, Keras, and there are even multilingual BERT models for more than 100 languages provided by Google Research. Now, when we have these pre-trained models, what we want to do with them is fine-tune them on specific tasks. Pre-trained models contain the structure of language, so they know how the syntax of the language is and the semantics of the language. We want to adapt these models now to perform certain tasks, for example, the sentiment detection in a review. We want to see whether a review is positive, negative, or neutral. So if you have the sentence, yet the act is still charming here, this is positive. This isn't a new idea, it's rather negative. And now we want this class label, instead of predicting whether something is the next sentence, we want it to predict a class like positive or negative. And again, of course, we're using a logistic regression. So what we can do now is we can add one layer to BERT, which is the classification layer. And when K is the number of classifier labels, and R is the size of the hidden state of this classifier token, we can use this layer to calculate probabilities for the labels, with a standard softmax, of course. And typically, the fine-tuning step is quite fast. So let's say we have less resources, we can take a pre-trained language model for English, for example, and fine-tune it to our task in the dataset which we have. 2 or 3 epochs could take approximately an hour on a TPU or GPU, depending on how much data we have. Now, as said, BERT has around 340 million parameters and was released in October 2018. Here you can see that a lot of models have been released with larger parameter sizes, but also recently DistilBERT has been released, which only has 66 million parameters. And it has almost the same performance, at least as the base BERT model. DistilBERT uses something called knowledge distillation. That means that the smaller, more compact model, the student model, tries to reproduce the behavior of a larger model, the teacher, in our case, the BERT base model. The training objective of the students is a linear combination of the distillation loss over the soft targets of the teacher, so it's trying to reproduce the soft targets that the teacher produces, and also the supervised loss on the training data. And DistilBERT generally has the same architecture as BERT, but with slight modifications. So we don't have these segment embeddings and this CLS token, these pooler tokens, and we reduce the amount of layers by 50%. So instead of 12, we only have 6 layers. DistilBERT was released by Sun et al., and the paper was called DistilBERT, a distilled version of BERT, smaller, faster, cheaper, and lighter. And as the authors show, if we train DistilBERT for 90 hours on 8 60 gigabytes V100 GPUs, so these are smaller than the TPUs used by Google, then we reach approximately the same performance as the base BERT model. Still, this is really, really resource heavy. But at least in 60% of the time, we can reach 97% of the performance. BERT can be used for multiple applications, and 2 things which we have in our NLU showroom, which rely on BERT models, are the aspect-based opinion mining demo, which detects in sentences as the coffee was warm and the cake was tasty, it detects which aspects of a restaurant we're talking about, in this case the coffee and the cake, and what our opinion is about this. And as you can see here, this is highlighted in green, so this is a positive sentiment, and the opinion 0 is linked to aspect 0, and opinion 1 is linked to aspect 1. In the second sentence, we say, the food was good, but the service was not friendly. And we can see again that unfriendly and service and good and food are linked to each other. But here the sentiment was detected to be negative. And the linking, the aspect and opinion extraction and the sentiment detection here is based on BERT models, German BERT models in this case. In addition to releasing this demo, we're also going to release the data set which we annotated to train these models on, and hopefully in the near future also the models. Another task, which is very important in information extraction, is relation extraction. And here again we can use modified BERT models. So let's say we have two entities, like Steve Jobs and Apple, and we say Steve Jobs, back then the CEO of Apple, always wore a turtleneck. And now this model recognizes that there's a certain relation between these entities, and namely, it's the relation organization leadership. This is really important if we, for example, want to systematically extract information from news texts or documents. So I think it's time for a third question round, and this time it's about BERT, before we start with the last part of the presentation. So, question 3. Which of the following statements about BERT are true? A. BERT only takes a few neighboring words as context for its attention. B. BERT training is highly parallelizable. C. BERT is the decoder part of the transformer architecture. And D. BERT uses the same language modeling task as Elmo. Now, the last two models I want to show you are GPT-2 and GPT-3. And GPT-2 created a lot of fuss in the press. So the press was very aware of this model because OpenAI said that this model is possibly too dangerous to release because it could create fake texts at scale. So it could swarm us with fake news. GPT-3 was recently released and blows every model we've seen so far out of scale. It's much larger than anything seen before. So, in contrast to BERT, GPT-2 and 3 build on the decoder part of the transformers architecture. Because they don't have an encoder, they also don't have decoder-encoder attention. So we simply have this decoder layers, and of course we have multiple of them. Now, the model has been released in 2018 by OpenAI, and the paper by Redford et al. Describes it. And as the transformers model, it also relies on token embeddings and positional embeddings, so that the model can understand at which position which token appears. And this time, as in traditional language models, we are again trying to predict the next token. So not as in BERT, the central or a masked token which is missing, but rather the next token in a sequence. And GPT-2 has 1.5 billion parameters, in contrast to BERT, large BERT model, which has 340 million parameters. It has been trained on 40 gigabytes of text. That is 8 million documents which are taken from Reddit links. So Reddit posts with a comma of more than 3, or at least 3, have been crawled, and documents which have been linked in these posts have been crawled, and then the model was trained on this. And again, we use the Bipair embeddings as a token representation here. What GPT-2 is especially good in is zero-shot learning. That is, learning on tasks which it hasn't seen during training, or performing on tasks which it hasn't seen during training. And we can see this here on different language modeling tasks. GPT-2 scored state-of-the-art results in 7 of 8 specific language modeling tasks without being trained on the training sets of these tasks. So we have different metrics here, the accuracies, perplexities, etc. And in 7 out of 8 of the tasks, GPT-2 performs the best. The only one where it doesn't is the 1 billion words task, where it had to deal with shuffled sentences. Here's a sample input, and if you want to, you can pause the video here and read through this input and through the text that GPT-2 generated out of this input. So what GPT-2 will do is it will take this input and then step by step generate next words. And the text is impressive in the sense that it's very coherent, and GPT-2 often catches on things that it said earlier and doesn't lose track of the topic. Here is another sample of a Lord of the Rings style text, even using Lord of the Rings characters. And you can see that during training, GPT-2 must have seen some Lord of the Rings text because it is able to recognize that Legolas and Gimli are somehow related to Aragorn. Well, there are many similar examples of such outputs, which are quite impressive, but if you pay close attention, you can still see that they are not human-produced. Anyway, GPT-2 offers many possible usages. For example, it could serve as a writing assistant to give writers ideas. Maybe this would help to create the newest versions of the Song of Ice and Fire books. It could help to create more capable dialogue agents, so dialogue agents which could also come up with their own stories. And many more use cases. But OpenAI also hints at possible dangers. So it could be able to generate misleading news articles, fake news articles. It could be able to impersonate the style of other persons, of authors, or of people on Twitter. And OpenAI hinted at many more such dangers. The page talktotransformer.com sadly is not available anymore. In this page, you could have tried out the GPT-2 model. But in our NLU showroom, we will have a German GPT-2 model ready in the near future. So we're currently working on this. OpenAI, even though they said that the model is too dangerous to release, has by now released the full model. And you can also download it and experiment with it if you have the hardware to do so. Now, as you can see here, GPT-3 is way larger than all of the models we've seen so far. It is in fact 100 times larger, more than 100 times, than GPT-2. It's by far the largest transformer-based language model, or even language model, that has been released up to date. It has 175 billion parameters. Now, with GPT-3, OpenAI did something fascinating. So again, they trained it as a language model, and they used tons of text. But this time, instead of evaluating it on language modeling tasks, they also evaluated it on NLP and NLU tasks. And they did not do any specific fine-tuning. So in their paper, Language Models Are Few-Shot Learners, they demonstrate that GPT-3 is able to perform specific tasks without task-specific fine-tuning. They call it few-shot learners, which is quite misleading, because in fact they perform something called in-context learning. What does that mean? First of all, it means that they do not fine-tune the model parameters, but second of all, during inference, after the language model is trained, they input some examples of a task. For example, saying German Käse is English cheese and German goalkeeper is English, German Torwart is English goalkeeper. And then in the last line, they would enter something like German Tastatur is English, and they would leave it blank. And then they would evaluate the answer of the model. And you would be surprised how often the model outputs the right answer without being explicitly trained to do so and without having its parameters adjusted to do so. This is insane. As I said, one example is translation, and they test GPT-3 in multiple settings. First setting is the zero-shot setting, in which they just describe the task, say translate English to French, cheese is, and they would look what the answer is. Then they would do the one-shot setting, in which they say translate English to French and provide it with one example. All of this during inference with no gradient updates. Please keep that in mind. The last thing is few-shot, where they provide multiple examples. And this is very different than showing the model an example, updating the gradients and the parameters, showing another model example, updating gradients, and so on, and then in the end asking it a question. They're not doing these gradient updates. Now, the tasks which they perform on are, of course, still language modeling, but also stuff like closed book question answering, translation, common sense reasoning, natural language interference, and so on. And even addition of numbers. So they would write, what is 2 plus 3? And now, across almost all tasks, of course, the largest GPT-3 model that they trained was the best by far. The few shot setting works best, but the zero-shot model is almost always better than all other zero-shot or few-shot models, which were trained particularly on these tasks. And sometimes even the state-of-the-art fine-tuned models for tasks are beaten, which is insane. Surprisingly, the model can even do simple calculations well in the 2 to 3 digit number region. On the right side, if you want to pause, you can see a task in which GPT-3 sees an example of how to use a made-up word, and then it gets the task to build a new sentence with a new made-up word, and it does so surprisingly well. So it does so in very, very good quality. I would highly encourage you to look at other examples of what GPT-3 is capable of. And because versions of GPT-3 have already been released, or at least some people have gotten access to them, I also encourage you to look up what people have been doing with GPT-3, including tasks such as code completion or even JavaScript website generation. Yeah? So this is really, really impressive what OpenAI has done here. Now, last but not least, I want to show you our NLU showroom. And I want to give you a demo of what you will be able to do in the NLU showroom. And as I said, we will be expanding the NLU showroom over time. We will add datasets, annotated datasets, which we ourselves annotate, and also models to the showroom. So we hope that it will be a valuable resource, especially for natural language understanding in the German language. Now, this is how our showroom looks. As you can see, it's part of collaboration between Fraunhofer IAIS and the Competence Center for Machine Learning. And we have different tasks available on the sentence level and the word level. And currently we selected German models. So I can input, for example, here in aspect-based opinion mining, a review of a restaurant. So I could say, das Filet war sehr lecker, aber der Kellner war etwas langsam. So the filet was very tasty, but the waiter was a bit slow. And now this is sent to our backend, and different BERT models actually process this. They realize that there are two aspects here, the filet and the waiter. And they also found different opinions, sehr lecker, very tasty, and a little slow, which funnily enough is here mentioned as two opinions, but it's correctly linked to the waiter. And it's correctly recognized also by a different word model that this here is positive, this relation, and this relation here is negative. So in the showroom, you will be able to enter your own texts or to select some pre-selected examples. Now let's look at relation extraction. So relation extraction is of course a different model. In relation extraction, we want to extract relations between certain entities. And here, for example, we have entities which concern companies. So I could say something like, Sven Giesselbach ist der Leiter des Natural Language Understanding Teams. So Sven Giesselbach is the team lead of the Natural Language Understanding team. And I mark here entity 1 and entity 2, and now I wanted to find relations between these entities. Let's see what it says. And it correctly found that this is the relation organization leadership. So it correctly recognized that I am the leader of the organization called Natural Language Understanding Team. Again, here we have a BERT-based model. So this is a separate BERT-based model. And again, you can enter your own text here or choose from examples. And we will give a bit more of a detailed description of what kind of relations we've trained our model on and what kind of entities we are able to process. Now, the last thing I want to show you is the sentence similarity. Now, here I can enter source sentences and target sentences. And a source sentence could be natural language understanding ist ein Teil von natural language processing. So natural language understanding is a part of natural language processing. Let me copy this for a second. And here we say NLU is a part of NLP. And ist ein Teil natürlich, ist Teil von. And here we can say natural language ist Englisch für natürliche Sprache. So the first sentence and this first sentence should pretty much correspond to each other, and the first sentence and the second sentence should be similar but not quite the same. And here we can actually see that some of our models got confused. So our Word2Vec model actually got confused and said that the second sentence is closer to the first sentence. But all of the other models realized that the first sentence actually corresponds more closely to this source sentence. So this is also one aspect which I like about this showroom, that you can explore how different models behave. Let's switch to the word level. So as you can see, we currently only have one task in the word similarities, in the word level. And this is word similarities. Let me zoom in a little bit here. So it has this rather cryptic name right now of engrams.de, which we have to replace, of course. But what are engrams? We've seen character engrams, so multiple characters in a sequence. And now word engrams are multiple words in a sequence, or phrases. One example could be New York City. And why don't we start off with New York City? And if I enter New York City, I get responses from Word2Vec, GloV, and FastText model. GloV and Word2Vec are very related. And what we can see here is that all three models output New York as a similar word or phrase, but then the responses quite differ. So FastText, which relies more on morphological information, has the plural, or New York, which is a very commonly used phrase, while Word2Vec and GloV have different other cities as related. So Chicago comes second in Word2Vec, while it's fourth in GloV, and only, I think, 7th or 8th in FastText. And here you can see that although all three models have been trained on the same corpus, they have a different perception or a different concept of context. And it makes a lot of sense to play around with this. And as soon as the showroom goes online, you can, of course, enter arbitrary words here. So maybe you're a fan of football, or as some call it soccer, as I am. So you could input the Champions League here. And you would find UEFA Champions League here, Europe League, UEFA Europe League, and particular seasons here in FastText. So this is quite interesting. So there are many ways you can experiment with the models, with the tasks here on the word level or on the sentence level. And I encourage you to explore these models once the showroom is online. And we'll be very happy to present you the showroom, hopefully by mid-September or the end of September. I hope you like this talk. If you have any questions, I'm happy to answer them. And yeah, don't be shy, feel free to ask. And thank you for listening.